So today we are going to discuss about the protecting group in organic synthesis. Myself Dr. Priyodip Das, Research Associate Professor, Department of Chemistry, SRM Institute of Science and Technology. So now what are the challenges in organic synthesis? Here we have discussed about the chemoselective reaction. You can saw the first one, this molecule have both aldehyde as well as primary alcohol group. So when it is oxidized, you use a chromium trioxide in presence of H2O. This is a non-selective path. Both the aldehyde and the primary alcohol group is converted into carboxylic acid. But when the oxidation can be performed in presence of silver oxide, then the aldehyde group is oxidized to carboxylic acid, but the primary alcohol group is remain unreacted. So this is the selective functionalization of polyfunctional molecule is an important and desirable attribute to the multi-step organic synthesis. So now we have come to the definition. What is the protecting group? So a protecting group is a molecular framework that is introduced onto a specific functional group in a polyfunctional molecule to block its reactivity under reaction condition needed to make modification elsewhere in the molecule. So if the molecule have several functional group, we have to use a particular reagent that can block this part, one of the particular functional group, so remain other functional group can take part in the reaction. So that will be the one example. If the R, this is the functional group, this is free, and now we give the protecting group. Now the RFGPG, it can mark the functional group and making it unreactive. Now we can discuss what about the quality of a good protecting group in organic synthesis. So a good protecting group should be such that it should be readily and selectively introduced to the desired functional group in a polyfunctional molecule. And it should be stable and resistant to the reagent employed the subsequent reaction step in which the group being masked. And is also desired to remain deactivated. It should be capable of being selectively removed under mild condition where its protection group is no longer required. That means it can mask the group, and it can, when the other reagent is introduced to complete the organic synthesis, it should not interfere in this reaction. After completion of the reaction, when we don't need the protection group, we have to put some mild condition so it can deprotect and take part further additional reaction. The protecting group must fulfill a number of requirements. So whatever the protecting group we are using in organic synthesis, they have to fulfill several requirements. What is the first requirement? The protecting group reagent must react selectively, that is the kinetic chemoselectivity, in good yield to give a protected substrate that is stable to the projected reaction. So whatever the next reaction should be carried out within the molecule, it should be protected. It should not interfere. The protecting group must be selectively removed in a good yield by relatively available reagents. So the protecting group, what are these? This can be easily removable by introducing some specific reagent, and the protecting group should not have additional functionality that might provide additional sites of the reaction. So protecting group in such like that they should introduce the additional functionality in this molecule, so make the next organic transformation be complicated. So now we are going to discuss about the building the case for protecting group. So how the protecting group can be introduced in a molecule. Let us see the first example. In this molecule we have two functional groups. One is the secondary alcohol, another is the primary alcohol. Now we want to convert the secondary alcohol into ketone, remaining the primary alcohol unintact. So what will be the strategy? The primary alcohol are more reactive since they are less hindered. That's why what we have to do, we have to introduce a protecting group for the primary alcohol, which should not protect the secondary alcohol. Now we should use the oxidizing agent that can convert the secondary alcohol into the ketone like PCC and PDC. Then finally the removal of the protecting group, and we will get the primary alcohol back. So note, however, that each the protecting group incorporated in a multi-step synthesis increases the synthesis by two non-productive steps, reducing the overall yield and efficiency of the synthesis. So the most reactive functional group commonly requiring the protection reaction means in organic synthesis the most reactive functional group is the alcohol, aldehyde, ketone, carboxylic acid and amine. So we need to protect this functional group during the several organic transformation in a particular molecule. The commonly encountered functional group in organic synthesis that are reactive to nucleophilic or electrophilic reagent whose selective transformation may be present. Several challenges to do regularly require deactivation by masking with a protecting group. That is the requirement to make to this several functional group in the molecule present. We have to mask and demask them due to the several transformation we need to carry out for that particular organic molecule. Now let us consider this example. In this molecule, this OH represented by the pink color is the acidic hydrogen, and if we give the magnesium ether, it will not produce the Grignard reagent. And here also we have two functional group. One is the ketone, another is the ester. And if what is the reagent that we give that can particularly reduce the ester into alcohol but not ketone, that is we need a protecting groups here. So if we see the pictorial representation, if we give the particular reducing agent lithium aluminum hydride to reduce the ester group into primary alcohol, we have to mask the ketone so that this lithium aluminum hydride cannot reduce the ketone group into corresponding secondary alcohol. So that is the strategy we have to impart by using the protecting group. Now we are going to consider about the protecting groups for alcohol. The common protecting groups for alcohol are ether protecting group. Ethers are among the least reactive of the organic functional group. So alcohol going to convert it into the ether. So how the alcohol going to convert into the ether? The ether protecting groups of alcohol can be grouped into following categories. First is the silyl ether protecting group. So we have to convert this alcohol into the silyl ether, and another is the acetal protecting group. So this is also we have to give some reagent that can convert the alcohol into the acetal, and this protection replace the acidic proton of an alcohol with an unreactive ether moiety. Then we have to give particular demasking agent so they can again back the silyl ether to alcohol and the acetal to alcohol. Now we have seen the common silicon based protecting group for alcohol: trimethyl silyl, triethyl silyl, tertiary butyl dimethyl silyl, that is TBDMS, and tertiary butyl diphenyl silyl, the TBDPS. All this silyl protection can be used to convert this alcohol group into this ether moiety, silyl ether moiety. So several functional group already used. So this, when the alcohol group is no needed for further reaction, then we have to use this silyl protection to convert this alcohol into silyl ether. And the silicon based protecting groups for alcohol, what is the simple reaction? The ROH, this the alcohol is going to react with this trialkyl silyl halogen in presence of a base to convert that silyl ether. And here this halide means basically we are used to get chloride or OTF, the triplet moiety. That is a very good leaving group. And now what is the basis we should use for that transformation of the alcohol to the silyl ether? Pyridine, DMAP, 2,6-lutadine and imidazole. Now if we see the reaction mechanism using tertiary butyl dimethyl silyl ether. So alcohol is there, we can give TBDMS chloride and imidazole as a base, and we can get the silyl ether. So what is the first? This oxygen lone pair can going to attack the silicon center, and oxygen silicon bond is more stable than the silyl chloride bond. So silyl chloride bond is going to break, and this is the species produced with oxygen as a positive charge. Finally elimination of a HCl, because this proton can be abstracted by the imidazole base, and finally we are getting the imidazole HC, imidazolium chloride, and we getting the silyl ether. And now example, this is the molecule. So in this molecule one chiral center is there, and this is the particular enantiomer. When it react to the TBDMS imidazole, it can produce the silyl ether or OTBDMS. And this is another example. If we have a molecule where both secondary and primary alcohol group is present, and if we use one equivalent of TBS chloride in presence of imidazole as a base, as the primary alcohol is more reactive than the secondary alcohol, the primary alcohol group is protected by the TBDMS ether, but not the secondary one. So now we are going to discuss about the deprotection of silicon based protecting group. So what are the reagent we use? Simply hydrofluoric acid. It's a very strong acid. So what it will do, it can break the ether bond, and here you can see that F minus is going to react with the silicon center and make a hypervalent silicon compound where fluorine is attached and silicon is negatively charged. And this hypervalent silicon compound can break the RO bond and produce the alkoxide anion, and this alkoxide anion take the H plus, which is eliminated from the HF, and return back the alcohol. So that is the fluoride sources that we should use for the breakage of this silyl ether linkage. One is the tetrabutyl ammonium fluoride, pyridine hydrofluoric acid, and hydrofluoric acid itself, and ammonium fluoride NH4 plus F minus. So all this fluoride reagent that can react with the silyl ether to produce the hypervalent silicon compound, which is break and produce the alkoxy anion, and the alkoxy anion after absorption of proton can produce the alcohol. So now we are going to discuss about the synthetic application of silyl protecting group. So the bulkiness of this TBDMS, the tertiary butyl dimethyl silyl, or TBDPS, tertiary butyl diphenyl silyl ether protecting group, can be used to advantage to suppress the hydrogen bonding to the oxygen restricting and any incoming reagent to approach from the least hindered or statically least hindered side of the molecule. Now let us consider this example. That is the TBDMS chloride imidazole we are going to use for the protecting this alcohol group. This is the secondary alcohol group, and now the secondary alcohol group is above the plane. Now we are giving metachloroperbenzoic acid, which can produce the epoxidation. And what is happening? The epoxidation can be happen from below the plane, because this is a bulky group is already plane in the above the plane. So epoxidation is preferred to take place from the below the plane. Now, if we use the tertiary butyl ammonium fluoride, the deprotecting reagent, it can convert the silyl ether into a secondary alcohol. But if we use metachlorobenzoic acid directly without the protecting of the alcohol group, then the epoxidation can be happen from the top of the phase, because that time this OH is not that much of bulky group, and this hydrogen attached to the alcohol group can also take part in the intermolecular hydrogen bonding with the epoxide ring, prefer the attack from the forward side. So the protecting group can clearly change the direction of the reaction. So now we are going to discuss about the bulkiness of the TBDMS group and DPDMS group ether protecting group that can also exploited in the incorporating the protecting group on less sterically hindered side of the primary hydroxyl group. So what is happening if we consider the first example? Here both secondary and primary alcohol group is there. So if we give TBDMS chloride 1 equivalent and imidazole in presence of a base, then primary alcohol group is more reacting than the secondary alcohol group. That's why it is get protected, and the secondary alcohol group is remain free. So now we are using pyridinium chlorochromate is oxidizing agent which can convert it, the secondary alcohol into the ketone, and further we are using TBDF, which can deprotecting the silyl linkage and produce the primary alcohol back. So this is the simple strategy where we can involve the less reactive secondary alcohol group in presence of more reactive primary alcohol group for further oxidation. So now we are going to discuss about the benzyl ether protecting group, which is another protecting group for alcohol. So rarely are the alkyl ethers used as a protecting groups for the alcohol, but benzyl ethers are special. So this is the structure of the benzyl ether, ROCH2PH. This is the benzyl ether. We can in abbreviation we can write the BN, and the formation sodium hydride we can use as a base in presence of a benzyl bromide, PHCH2Br, and it can produce the benzyl ether molecule, or we can give ROBN. Now this hydrogenolysis of this selectively used to clip the benzyl ether protecting groups. So this is the deprotection of the benzyl ether, where we can hydrogenolysis can be happen in presence of hydrogen and palladium carbene, which can convert it this benzoyl ether into alcohol and toluene. So now we are coming to the most interesting cyclic acetyl protecting groups. So this is the acetonoid protecting group for 1,2-diol. So here you can give a 2-diol the consecutive alcohol molecule in the two adjacent carbon atom, which is react with the ketone in presence of para-toluene sulfonic acid, and that produce the acetal. So other sources of this protecting group is there. This is the 2,2-dimethoxypropane that can also produce the similar acetal protection, and this is only applicable to the diol molecule. Now, what is the condition that can cleavage this acetal into diol and the ketone back? This is the either it can done by the acid catalyzed hydrolysis. Such as reagent we can use HCl water or acetic acid water. So acid catalyzed hydrolysis is the condition to convert this acetal into diol. So simply this protecting group is used for the diol. Suppose a molecule of diol, another functional group, we have to protect the diol, we have to use the para-toluene sulfonic acid and ketone that can produce the acetal, that is the protection of the diol, and we are make acid catalyzed hydrolysis of the acetal to get back the diol for further transformation. Now we have seen the synthetic application of the ether protecting group. That is the perspective on their synthetic application, how the ether protecting group can be used for the organic transformation in a particular molecule. Now let us consider the molecule where we have seen a secondary alcohol group and the more reactive primary alcohol group. And if we give TBDMS chloride, that is a silyl ether protecting group, in one equivalent in presence of imidazole base, it can convert the primary alcohol into OTBDMS, and the secondary alcohol remain unreacted. Now if we give sodium hydride in presence of benzyl bromide, another alcohol protecting group, then this secondary alcohol is converted into O-benzoyl protectant. So now the secondary alcohol and primary alcohol are both protected by ether protecting group, but they are different ether protecting group. Now we have to use the demasking reagent or deprotecting reagent selectively. So first we are using TBA, tertiary butyl ammonium fluoride, which can convert the primary silyl group into primary alcohol. And then if we give PCC, pyridinium chlorochromate, the primary alcohol group converted into aldehyde. Then we can give hydrogen palladium carbon, which can remove the benzoyl protection and get the secondary alcohol back. So this is a strategy where we have to convert the primary alcohol, or we have to oxidize the primary alcohol in presence of a secondary alcohol remains unreacted. So this is the strategy should be employed for this purpose. Now we have another synthetic application of the cyclic acetal protecting group. Now we have see this is a D-mannose, this is a carbohydrate where the terminal group, one is the aldehyde, another is the primary alcohol. Now if we give sodium borohydride, is a reducing agent that can convert the terminal aldehyde group into primary alcohol. And now we can write, this is in the zigzag formula where you can see the different chiral center in the molecule. Now we can see in this molecule have cis or trans diol, that is the alcohol group in the consecutive carbon atom. So if the diol protection, we already know that para-toluene sulfonic acid in presence of a ketone, so it can produce the terminal diol converted into acetal. And then if we give sodium periodate H2O, then it can cleavage the diol and produce this chiron in the asymmetric synthesis. So this is a very important reaction. So as we see, the primary alcohol is more reactive than secondary alcohol. So in this molecule there is actually 4 secondary alcohol and 2 primary alcohol. So when we try to protect the diol through ketone using para-toluene sulfonic acid, the primary alcohol should be involved in the formation of acetol. That's why in the middle, these 2 alcohol group which are on the same side, that is a cis diol, cannot be take part in the acetal formation, but the terminal alcohol group, both primary and secondary, it take part in the acetal formation and produce this molecule. And when it is going to cleavage in presence of sodium periodate, it is produce a chiral synthon in the asymmetric synthesis. Now we are going to consider another reagent, that is the tritryl ethers, the triphenyl methyl ethers. So this is the triphenyl methyl ethers or ROTR, that is a selective protection. Now when this protection should be used, if we have a molecule like this, we have both secondary alcohol as well as primary alcohol, then we can use this triphenyl methyl chloride in presence of triethylamine and DMAP as a catalyst or base in dichloromethane solvent. So as we know that primary alcohol is more reactive than secondary alcohol, obviously the primary alcohol go for the protection, and we are getting secondary alcohol. This should not protect the secondary alcohol. 100% conversion with the primary alcohol protection. Now cleaved by acid or hydrogenolysis, so we can give this protection can be removed either by the acidic hydrolysis, or we can also perform hydrogenolysis in presence hydrogen in presence of palladium carbon. So both this reagent can remove the OTR protection and back the primary alcohol, but this should not be applicable for the secondary alcohol. So in this case we have shown the selective deprotection strategy. So we have in this molecule several alcohol group which are protected by several protecting group, OTHP, OTBS, OEM, and we have to use several deprotection condition. So first, if we want to protect the TBS, OTBS group, we have to use tertiary butyl ammonium fluoride. If we want to deprotect the THP group, then we have to use acetic acid in presence of H2O or THF, tetrahydrofuran. And if we want to remove that OMEM protecting group, we have to use TiCl4 or ZnBr2. Now here we shown the another MEM protection group of the alcohol. So this is also a ether protection, but it's a long chain ether. So this is also used for several purpose and can be short term is the ROMEM, and this is also a long chain ether. Now we have seen that ROH, the alcohol group, when treated with the base sodium hydride can abstract the proton of the alcohol and alkoxy anion is produced, sodium alkoxide. Then when it react with the MEmCl, it can produce ROMEM. And when the ROMEM react with the ZnBr2 or PPTS in tertiary butanol, it can give the alcohol back. So this is the basically the protection deprotection strategy using MEM. And here is an example where we have the two alcohol group. One is the normal secondary alcohol group, one is the allylic alcohol group. Allylic alcohol group have a protection of OTHP, and this normal secondary alcohol group has a protection of MEM. And if we use acetic acid or acidic hydrolysis for the deprotection or demasking reagent at room temperature, then the allylic alcohol group is get deprotected, but the OME group M group is still remains same. And this is the PPTS structure of the PPTS, the pyridinium's paratoluene sulfonate. So this can be used instead of ZnBr2 to remove the MEM protection. So now we are going to discuss about the use of carboxylic acid ester as a protecting group for alcohol. Because we know that when an alcohol reacts with a carboxylic acid is produced ester. That's a very well known reaction. So this strategy can also used for the protection of alcohol. But this strategy is limited since they undergo acyl substitution, hydrolysis or reduction. So they have some, this protection technique have some limitation because we know ester can easily hydrolyze, and getting the alcohol and acid back, it can undergo for reduction to primary alcohol again. Now we have an example here. This is the alcohol group with SiMe3 and a double bond is there. So when it's treated with acidic anhydride in presence of a base like DMAP or triethylamine, DMAP are actually used as a catalyst and triethylamine as a base. So what is happening, the alcohol group can produce the ester. The 100% yield is there, and the deprotection of ester is usually done under basic condition, not acidic. So now we have seen a typical molecule where we have three alcohol group is there. Two are secondary alcohol and one is primary alcohol. And this in the secondary alcohol group are on the opposite side of the plane. One is above the plane, one is below the plane. So if we give tertiary butyl acyl chloride in a solvent of pyridine and a mixture of dichloromethane at room temperature 0 to 25 degrees centigrade, then the primary alcohol group is get protected. It got ester protected. So that is the 5-valent ester. This is the resistance to nucleophilic attack including hydrolysis under mild basic condition, and it can be cleaved using metal hydride reagent. So under mild basic condition, it cannot be hydrolyzed. This ester, the pivalate ester, is not going to any hydrolysis under mild basic condition. So if we want to demask or deprotect this pivalate ester, we have to use metal hydride reagent, and that reagent is very important for several organic transformation in carbohydrate chemistry. Now if we saw the example of the selective esterification, we have seen the acyl chloride 1.2 equivalent and 2,4,6 cholinidine 2 equivalent that can be used as a base. So it is usually protected, and we get more than 99% monoacetate, 99% monoacetate group, where the primary alcohol group CH2OH get formed the ester, and we have seen that 78% yield we are also getting where the other secondary alcohol group has remained unreacted, and this is the structure of 2,4,6 cholinidine. So this is the another protection, acetal protection, tetrahydropyranyl ethers. This is also used for the alcohol protection. It is readily introduced by reaction of enol ether dihydropyran with an alcohol in the presence of an acid catalyst. And what are the acid catalysts used for this purpose? Paratoluene sulfonic acid, BF3, POCl3. So we have seen the protic and Lewis acid both are used for that purpose. So THP group is readily hydrolyzed under aqueous acidic condition, not its basic condition. Remember this. And with acetic acid, THF, paratoluene sulfonic acid, and DOXH, this is a cation exchange resin that can give the cation, that the H plus, which can also use for the deprotection of this THP. And now we have seen one reaction where the dihydropuran and enol ether can react in the PPTS. We have seen the structure of the PPTS, that is the paratoluene pyridine sulfonate in presence of dichloromethane, and how the reaction happen. The ROH can going to attack at this bond, and where oxygen is positively charged, so this bond can go for a shift where oxygen is become neutral, because oxygen is more electronegative than carbon, and this is the tetrahydropyranyl ether and acetal, and we are getting 100% yield for that reaction. And this is the diastereomer are also possible, so because this is a chiral center, so we can get stereoisomer for that. And let us see the structure of the PPTS, which I have also seen for the last slide for the conversion or for the deprotection reaction. So still now we have discussed about the several protecting group for alcohol: silyl ether, benzoyl ether, THP ether, OMe ether, and also this THP protection. So in organic synthesis, the 2-tetrahydropyranyl, the THP group, is used as a protecting group for the alcohol, that we have already seen. And the reaction of the alcohol with the DHP forms a THP ether, protecting the alcohol from a variety of reaction. So if it is protecting the, if we use this protection in alcohol for the primary or cyclic alcohol also, that can avoid several reactions for the alcohol group. That is our main objective of the protection of the alcohol group. So this reaction of the alcohol with DHP from a THP ether, protecting the alcohol from a variety of reaction, and the alcohol can later be restored by acidic hydrolysis, concomitant with the formation of the 5-hydroxypentanol. So if you see the reaction here, we can easily see the ROH can reaction with the DHP, and we have seen this protection reaction. And finally, in presence of paratoluene sulfonic acid in dichloromethane, we have used as a solvent, and it can back this molecule, that is the 5-hydroxypentanol is also produced, and we can keep this is the chiral alcohol, and we get a single diastereoisomer. In this conversion, that stereoselectivity is also introduced by using this protecting reagent. So now